From the port of Rotterdam in Europe, to Shanghai in China, and Singapore in Southeast Asia, you will find nearly identical shipping containers everywhere. What's surprising is that about 95% of the world's shipping containers are manufactured in China, and over 80% are produced by just 3 companies. Inside the largest factories, a new container rolls off the production line every 6 to 8 minutes. So how is a steel container weighing several tons actually made? And why does global trade depend on just a few factories to produce it? That is exactly what we are going to explore in this video. Before 1956, cargo was loaded and unloaded by hand, one bag and one crate at a time. A single ship could spend weeks in port. That year, a trucking entrepreneur named Malcolm McLean launched the first container ship, carrying 58 standardized steel boxes from Newark to Houston. The cost of handling cargo dropped from $5.83 per ton to just 15.7 cents per ton, making it nearly 40 times cheaper. That was the beginning of containerization. As the system spread around the world, demand for these steel boxes grew faster than ever before. Manufacturers in the United States, Europe, Japan, and South Korea gradually lost their advantage to producers with lower costs. By the 1990s, container manufacturing had shifted to China, and it has largely remained there ever since. But before a container can appear on a ship, a truck, or a train, it begins its life as a giant coil of steel. A shipping container in Rotterdam looks exactly the same as one in Singapore. That's no coincidence. A shipping container is much more than just a steel box. It is a global standard. ISO standards define everything, from its dimensions and load capacity to its identification codes and corner fittings. Because of these standards, a crane in Europe can lift a container made in China without needing to know which company built it. Today, more than 40 million shipping containers are in use around the world, and every one of them follows the same engineering language. That language begins with the material used to build the box itself: steel. Not every type of steel is suitable for building a shipping container. A container must withstand seawater, snow, extreme temperatures, and more than 20 tons of cargo for many years. That's why manufacturers use Corten steel, a name derived from corrosion resistance and tensile strength. What makes Corten steel unique is that when it is exposed to air and moisture, it forms a thin layer of rust on its surface. Instead of continuing to corrode the metal, this rust becomes a natural protective barrier. Each 20-foot shipping container requires about 1.5 to 2 tons of Corten steel. The material arrives at the factory as massive steel coils weighing tens of tons. These coils are slowly unrolled like giant rolls of paper before being cut into flat steel sheets. But a flat steel sheet cannot become a container wall just yet. It is first cleaned with high-pressure abrasive blasting to remove rust, oil, and other impurities. The sheet then passes through corrugation rollers that form its distinctive wavy pattern. Those corrugations are not for appearance. They are pure engineering. By shaping the steel into corrugations, its stiffness increases dramatically without adding extra material, using the same principle as corrugated roofing sheets. Corrugated walls make a shipping container much stronger, but the components that truly determine the strength of the entire structure are the 8 small cast steel blocks located at its corners, known as corner castings. Each one measures only about 178 by 162 by 118 millimeters. Yet a shipping container is designed to carry its loads through these corner points, not through its walls. When a crane lifts a container, the lifting force passes through the corner castings. When containers are stacked aboard a ship, most of the weight from the containers above is transferred through these castings and the corner posts connected to them. The side walls, roof, and end panels carry very little of the load. According to ISO standards, every shipping container must withstand a stacking load equal to about 8 times its maximum gross weight, approximately 244,000 kilograms, with the entire force concentrated through just 8 hand-sized corner castings. On the world's largest container ships, containers can be stacked as high as 10 levels. What keeps them securely in place isn't ropes or chains. It's the engineering behind those 8 corner castings. Once the steel panels have been formed, assembly can begin. And this is where the factory starts to look very different from a traditional workshop. Rows of robotic arc welders work simultaneously, each arm moving along the corrugated ridges of the container panels with a level of consistency that would be difficult for a human to maintain continuously. The primary welding method used is mag welding, or metal active gas welding, which is well suited for thick structural steel and high-strength load-bearing welds. What many people do not realize is that a completed shipping container contains hundreds of meters of welds. A single side panel alone can require dozens of meters of welding. And if just one critical structural weld fails, the load-bearing capacity of the entire container can be affected. That is why, even though robots perform most of the welding work, human workers are still present at every station. They position the steel panels, inspect the welds, and handle details that machines cannot yet fully replace. While the container walls are being welded together, another process is taking place at the same time below them: the installation of the container floor. One detail that many people overlook is that although most of a shipping container is made of steel, its floor is usually made of wood. The floor frame is built from welded steel I-beams. This structure directly supports the cargo inside the container and serves as the surface that forklifts drive across every time goods are loaded or unloaded. On top of the steel frame sits the wooden floor, and not just any wood can be used. Traditionally, manufacturers have relied on keruing or apatong, 2 tropical hardwoods from Southeast Asia. At around 28 millimeters thick, these boards are strong enough to withstand forklift traffic for years. A container floor must be capable of supporting loads of up to 30 tons without cracking or sagging. In recent years, supplies of keruing and apatong have become more limited. As a result, many manufacturers have switched to bamboo plywood, a material with similar strength that can be replenished much faster than tropical hardwoods. Before installation, the wood is treated with chemicals to prevent termites and decay. It is then cut into long boards that run the length of the container and secured to the steel frame below. It may seem like a simple component, but it must meet international quarantine requirements before the container can enter ports around the world. Once the floor frame, wall panels, roof, and doors have been fully assembled, the container finally begins to look like the one you would see on a ship or a truck. But before it can leave the factory, it must pass 2 final stages. The first is painting. The container is coated with an anti-corrosion primer, followed by protective top coats on the exterior. Workers use HVLP spray guns to manually paint corners and hard-to-reach areas that automated systems cannot easily access. Then comes inspection. And this is far more than a simple visual check. During the stacking test, the container must withstand enormous loads from other containers stacked above it, simulating conditions aboard the world's largest container ships. In the lifting test, the entire structure is lifted using only its 8 corner castings, exactly as it would be handled by cranes in a port. The racking test twists the container frame in multiple directions to recreate the forces experienced during ocean transport. Finally, the water tightness test examines every weld and opening to ensure that not a single drop of water can enter the container. Only after passing all of these tests can a container receive CSC certification, the mandatory approval required for international transport. If shipping containers are so important to global trade, why has most of their production become concentrated in a single country? The answer was not the result of one decision. It was built over decades. Low-cost steel, abundant labor, a highly integrated domestic supply chain, and the ability to expand manufacturing capacity at a pace few countries could match. When global demand for containers surged after the 1990s, China was the only country capable of supplying them at that scale. Today, CIMC, Dongfang, and CXIC control more than 80% of global container production. In 2021, Maersk agreed to sell its refrigerated container manufacturing business to CIMC for nearly $1 billion. However, the deal was never completed after facing opposition from U.S. competition regulators. It is just a steel box, yet it became important enough for a government to step in. Looking back, a shipping container does not seem particularly remarkable. It is just a rectangular steel box with familiar corrugated walls and 8 small corner castings no larger than the palm of your hand. But behind that simple design are hundreds of meters of welds, technical standards accepted around the world, and a manufacturing industry so concentrated that just a few factories help determine the flow of global trade. Almost everything you use today has likely traveled inside a container like this at some point. And that container was probably built in a factory in China that you have never heard of, yet it remains an essential link in the system that keeps global commerce moving.